Hey everyone, so today I will be telling you about the activity of an isotope and half-life. So in case you do not remember, isotopes are elements with the same number of protons, so the same atomic number, but different number of neutrons, meaning that the mass number, the number on the top, is different. Now, when I talk about the activity of a radioactive isotope, I'm talking about the number of atoms or nuclei that decay per second. Sometimes the activity can be also per minute, okay? But let's just leave it as now as per second, okay? So the activity of a radioactive isotope is the number of radioactive decays that are happening in a certain amount of time. Now, in case you do not remember, when I have an unstable nucleus, or nuclei actually, if I want to talk it in plural, which I can call the parent nucleus, they are going to decay into another nucleus, okay, that is hopefully more stable. That's going to be called the product or the daughter nucleus. Now, if you look at the activity of several types of isotopes, you're going to see that as the nuclei decay, the number of parent atoms or nuclei go down, therefore the activity of the sample decreases, okay? So that means that the more you are decaying, the less active you are. So the number of nuclei that decay per second or per minute decrease. And if you draw a graph, this is how it looks like, okay? So you use a Geiger counter to monitor the activity of a radioactive sample and to measure the count rate. And in this graph, you have the count rates with counts per minute over time. And you see that it starts at 600 and it goes down in this nice shaped curve up to less than 75. Now, this graph has kind of a pattern. If you look at the graph carefully, you're going to see that every 45 minutes, something interesting is going to happen. The count rate is going to decrease by half. Look at that. 0 minutes, 600. After 45 minutes, I now have a count rate of 300. After 45 minutes, I now have half of 300, 150 as count rate. And after other 45 minutes, I have 150, half of that, which is 75, okay? So as you can see, every 45 minutes, every time that I have this specific amount of time, in this case for this isotope 45 minutes, the count rate decreases by a half, okay? And this changes depending on the isotope. So again, I got this graph and I got this did you know from AQA. So some radioactive isotopes have half-lives of a fraction of a second, when others have half-lives of more than 1 billion years. The nitrogen isotope N12 has a half-life of 0.0125 seconds, and the uranium isotope 238 has a half-life of 4.5 billion years. So the graphs always look the same, and you always have the trend that each half-life, which is what this is going to be called, this 45 minutes, each half-life, the count rate decreases by half. So now you probably can figure out, oh, let me show you this first. I don't know why I had this the other way around. So now probably you could figure out that the half-life can be defined as the number, so is the average time it takes for the number of the nuclei of the isotope in a sample, and therefore the mass of the atoms to halve, okay? Or for the count rate of the isotope in a sample to fall to half of its initial volume. So of course that as I have decay, the mass is going to decrease, and it decreases by half every time I find a half-life. The count rate decreases by half every time I have a half-life, and the half-life will be the average time it takes for things to halve, okay? So again, the half-life of an isotope is the time that it takes for the number of nuclei to halve, okay? And then you can get the number of atoms of a radioactive isotope and the count rates, they both decrease by half every half-life, okay? So basically everything happens in a half-life, everything decreases by half. Mass, the number of isotopes that you have in there, the activity of the sample, okay, all these things. So let's try this exercise. So again, this exercise I took from AQA. They show a graph, but you don't need the graph. Sorry, I just hit the microphone. you don't need a graph, and they just say you have 600 counts per minute in the first 45 minutes, you have 300 counts per minute in the next 45 minutes, okay, and they keep decreasing, so 600 to 300, 300 to 150. They say what it will be the count rate after 135 minutes from the start. So this is actually about the previous graph. But how would you do it? Well, you could see how many times I have 135 in 45, which should be 3. So that means I would have 3 half-lives. And I could simply do 600 divided by 2, 1 half-life. 300 divided by 2, another half-life. And then 3, which gives 150, and then 150 divided by 2, which is another half-life. I could be doing that, but I can as well, to make my life easier, instead of dividing by 2 every time I get a result for the exact number of times of half-lives, I could do the following. I could do 600, the initial count, divided by 2 to the power of the number of half-lives I have. So this would be the same as 600 divided by 8, and this would give me 75. So I can either keep dividing the stuff by 2, so each half-life I divide the result by 2, or then I can do that the overall count after n half-lives, and this is not half minus lives, okay? So the overall count after n half-lives is going to be equal to the initial count rate, 600 in this case, divided by 2, and then I get 2 to the power of the times that I would have to divide it for. In this case, 2 to the power of 3. Okay? So, I mean, it's up to you. You can use this formula, or you can keep dividing by 2. But if you have something like with 10 half-lives, maybe it's just faster. If you would do the count rate will be the initial count, whichever they would give you, let's say 500, divided by 2 to the power of 10. Okay? So, now that you know this and you know this part, I'm going to give you some exercises that I made them up, okay? So it says a sample has a half-life of 30 minutes. What is the count rate after 150 minutes if the initial count was 1,000? So again, I could figure out how many half-lives I have, so how many times 150 will be, or how many times, 150 fit in 30, and then figure out the number of half-lives. That's 5 half-lives, and I could either do 1,000 divided by 2 5 times, or then I could get that the count will be 1,000 divided by 2 to the power of 5, okay? And this would give me a number, all right? The next one, a sample has a count of 500 and the half-life is 10 minutes. What is the count rate after 6 half-lives? So again, I want the count, the initial count is 500, I have 6 half-lives, so I do the calculation, count equals 500 divided by 2 to the power of 6, okay? So this is pretty easy, okay? Sometimes they could ask for the initial count by giving you the count after a certain number of half-lives, so you may move around the exercises. So far I've seen what is the count, what is the time that it has been, and what is the mass. So just as the count rate will decrease, the mass will decrease. You can use the same formula, okay? Now let me just tell you something. The radioactive decay, and I told you this before, is random. It cannot be predicted, okay? So I cannot predict when an individual atom or nucleus is going to decay, but I can predict how many atoms or nuclei will decay in a certain time. So it's like, for example, statistics. When I throw dice, I cannot predict the number that I'm going to get next, but I can predict that after throwing the dice 100 times, that the number 6 will come up 1 in 6 of the times, okay? So 1/6 of the time, sorry. So I can only predict that this is going to happen, so each half-life I'm going to have half of the nuclei to decay, but I cannot say that the nucleus number 20 is going to decay in the next half an hour or in the next 5 minutes, okay? I cannot do that. And that is it for half-life. I hope it made sense. If it didn't, you know what to do. Up to my next video. Be happy and healthy. Bye!